Get started. Enable recording. So, Daniel?
Yep, sure. So hello, everyone. I'm Benny from UBC, and the idea today is to talk a little bit about my PhD work, which is on effective FPGA debug of machine learning applications. We don't have a huge crowd today, and I'm also not planning to use the entire 1 hour that we have available, so feel free to interrupt me as many times as you want, ask questions, and I also didn't want to make this talk overly technical, so it's more about the key ideas that we have in here, why we need to do on-chip debug, why we're focusing on machine learning applications, and so on. So, especially here in the FPGA community, we all know that debugging circuits is hard, and this is especially true for machine learning circuits, which are getting increasingly complex. Debugging those applications always gets more complicated by the fact that we have to do on-chip debug in many scenarios. Sometimes simulation may be too slow, sometimes bugs may only manifest when the circuit is running at speed on chip, as I'll show in the next slide. And we also know that tools for debugging a generic circuit, they already exist, but as I'll show you, they're far from ideal for machine learning circuits, right? Traditional on-chip debugs are things such as signal tap, which you're basically seeing there on the screen. And the idea is that they provide visibility by recording the behavior of the design as it runs at speed for later interrogation. So basically, first, as you can see there, step number one is you look at your RTL and you basically decide which parts of the RTL design you want to observe. So you insert instrumentation at this point. Then you compile your circuit, you put it on an FPGA, and when you put it on an FPGA after synthesis, you run it at speed. And while running it at speed, you're recording this information into some sort of on-chip memory. Normally you store it in a trace buffer, which is a fancy name for a circular on-chip memory. After recording everything, you stop execution, you retrieve all of this data, and you are able to replay the execution offline, looking at those beautiful waveforms in the way that we are already used to. However, a key limitation here is that the memory is often not big enough to record enough information on chip. And if you think about it, this is actually especially challenging for machine learning circuits. If you think about recording large weights and activations, for example, it's actually a big challenge only to fit those weights and activations on the FPGAs in the first place. Imagine just recording this values, like it's not really something that is feasible. So we have to do something different here. So I want to start this presentation with a motivational example, really to show you why previous techniques aren't enough for machine learning. And with this motivation example, I basically want to convince you of three main things. First, as you'll see here, some bugs may take a very long time before they either manifest or they become apparent. So this actually means that running the RTL simulation or recording all of the raw values over time are often not a good option at all. The second thing is that even if we know in which part of the execution the bug manifested or in which part of the execution we were able to observe the bug, sometimes observing that specific point in time is not enough. As I'll show here with this example, the correctness of a machine learning circuit may be very hard to determine. And as a result, it's not immediately clear at which part of the execution we should observe the circuit to understand the problem that we may be having. And this is a very big problem. And the third thing that I want to convince you here is that, as we all know, machine learning applications, they are commonly designed at a very high level of abstraction, sometimes using HLS tools, sometimes using tools such as TensorFlow and automatically mapping into RTL. And what this actually means is that sometimes the visibility in terms of the low-level hardware may not be as useful, especially if we're thinking about debugging the model itself, right? So the image below here is a good example of what I just described. So it's not the only use case, but it's a good example here. And in this example, I'm basically showing you a DNN. And this DNN is composed of a sequence of dense layers and relay activations. And we're assuming that we're using some sort of hardware accelerator to train this network. And one thing that I'm going to tell you here is that this network here for this example is intentionally designed to be small. And this is basically to allow me to train things on my computer. But in a more realistic scenario, the network could be very, very big, very, very expensive to train. So training on my computer will not be possible at all. We'll have to run this on some sort of accelerator, and all of the information that I'm going to extract here during the training process is also something that we'll have to extract on chip, right? And the interesting thing here about this example, as you can see, is that we're actually able to train the network really well for the first few epochs, but the accuracy actually suddenly drops after epoch 33, and then it recovers after epoch 44. So if I'm the researcher here that is developing this network, and if I see something like this during training, I definitely want to see what's going on, because this is not an acceptable behavior at all. So a cool thing to note here is that we'll not see something like this right away using RTL simulation, because we'll only be able to perform the first few training steps in RTL. We're not going to train an entire network using RTL at all. So at the RTL point of view, everything is fine. And software, depending on how we're doing this, if we're really emulating all of the bits and everything, it could behave very differently from the circuit with limited precision, especially if we're talking about training, right? So if we observe things on chip and we want to debug this, we would likely only see the progress of the training accuracy over time, which is this image that I'm showing in there. But we have no other information to help us diagnose the problem. However, there are many other interesting statistics here that we could use that could be very useful for understanding the problem. Any questions so far? Okay, if you have any, just feel free to interrupt me. So this image here is basically the same image that we had before. Right at the very top, that's image A, and the rest of them, they're basically statistics about the same training process, right? So if we look at the minimum and maximum weights gradients, for example, which is image B, you can see that they all become 0 around the same time that the accuracy dropped, which is interesting. It actually tells us something. Okay, so the gradients are 0 when the accuracy drops. And you can actually see the cause of it if you look at image E, which shows the activation sparsity of some layers. The activation sparsity of those layers, they actually become nearly 100% at around the same time that the accuracy drops. So if we actually correlate this information with the type of network that we have, we actually know that this is the dead ReLU problem. So we basically have ReLUs that are dying, and basically layers that have this problem will output nearly the same output for any given input. And once a layer gets into this state, they are very likely not going to recover, because the gradients of a ReLU at 0 is also 0. So takeaway here so far is that by looking at statistics, we're kind of able to understand what's going on, even though we don't have the raw information, right? But this is only one of the symptoms of the problem. And the symptom of the problem here is that the accuracy is dropping. And there are a couple of ways in which we could solve this, right? We can, for example, change the activation, use something like a leaky ReLU, for example, and then possibly our activation with a leaky ReLU will be our sparsity with a leaky ReLU will be very, very close to 0, which is going to solve this problem, but is also very bad if our accelerator profits from sparsity. So maybe we can try to observe this data a little bit more and try to see if we can understand it a little bit more. So another thing that we can see here is that the sparsity slowly goes towards 0, and you can see this in image E. And there's actually no batch of inputs that is solely the reason for the problem. So if we actually decided, okay, I'm going to pause the execution here, I'm going to observe right when the accuracy dropped to see the problem, we'll actually not see much there. We'll just see that the problem happened, but we will not know why, because things happen slowly over time. So we actually need to observe things for a long period of time. More interestingly here, you can actually look at image 1D, and you can actually see that the mean value of the activations actually start to significantly vary between batches after epoch 60. And this basically indicates that the network is possibly overdimensioned. So you can see those huge bumps in there. So the second image here shows a smaller version of the same network, and it basically avoids some drops of accuracy. It's still significantly sparse, and it has activations that don't significantly vary between batches. So we have a couple of takeaways here. Takeaway number 1, it's not immediately clear where we should start observing the circuit. So the long-term visibility that we have in here is actually very important. We cannot observe single snapshots. They're not going to help us as much. And 2, we're very often able to debug the model if we're observing the right kinds of statistics. So this basically means that we don't necessarily need to trace raw values to understand the behavior of a machine learning circuit or a machine learning model. So what we're proposing here is a little bit different from traditional on-chip debug. The main observation here of this work, which we published at FPGA 2019, is that we can use domain-specific characteristics of machine learning circuits to create instruments that maximize utilization of the trace buffer space while still providing information that is meaningful to an engineer. So in other words, we're recording domain-specific information about large tensors, large activations, large weights, instead of tracking the raw values. And as you see here, one of the main takeaways of this presentation is that we can store, at least in the worst case scenario, 21.8 times more information than in previous work. Actually, depending on the way that you're observing the data, you can actually record it for hundreds of times more, like thousands of times more than in previous work. And the main differences here so far are the domain-specific instrumentation, as well as the user interface. So let's talk a little bit about our debug instrument. So we know that machine learning applications consist of very large arrays, such as activations and weights. And all that our instrumentation does is to track those large arrays over time. So let's say, for example, that we want to check whether the weights matrix is spanning throughout the entire space that is provided by its bit width, for example. For that, we can use the distribution instrument, which generates a history of the distribution of the matrix we're tracing over time. Another thing that we might want to do is that we might want to try to detect an error that is causing some activations to clamp at a minimum or maximum value, for example. For that, we can use the spatial sparsity instrument, which basically records whether each specific element of the array is 0 or non-zero within a predetermined threshold. And we can also use the same logic to track elements that are close to 1, another upper bound, or even not a number. And in our FPGA paper, we also have other instruments, such as the summary statistics instrument, which basically allow us to track one kind of statistic per frame, such as sparsity, mean, or standard deviation of every single matrix for every single frame. And in this work, we also put in some effort on conceptualizing how the user will visualize the information that has been recorded by our instrumentation. And as you can see here, the main difference, the main takeaway is that we're not stepping through clock cycles as we would normally do in signal tap and in any other hardware-oriented debug flow. We're not stepping through lines of C code as we will do in a high-level synthesis-oriented debug flow. Instead, we're stepping through frames of the machine learning circuit. And what this actually means is that we have no access to the raw values of the matrices we're tracing, but we can trace the circuit for a substantially longer period. So this table here is our paper. Don't worry about most of it for now. I just want to highlight a few key things in here. So in this work, the name of the game, what we're really trying to maximize here is the number of times we're able to trace information about the matrix we're observing, right? And that's the number of trace frames that you can see in there. So if you compare this with previous work, even if we're tracing a very, very, very like ridiculously small 28 by 28 matrix, we'll only be able to store information about it for around 4 frames if we have like a reasonable sized trace buffer, which is definitely not enough depending on the bug that we have and depending on like for how long we actually need to observe the circuit to understand the problem. However, if you're happy observing the distribution of the matrix over time, or if you're happy observing the spatial sparsity of the matrix over time, we can record it for hundreds and hundreds of frames at a very low area and latency cost. Actually here, even if we combine all of those instruments, we can still track the same matrix for 87 frames, which is 21.8 times more than in previous work. So if you're interested about this here, you can have a look at our FPGA paper. So to make this presentation a little bit more dynamic and to really make sure that you understand the process, I decided to add a quick demo here. And in this demo, I'm basically going to go over the 5 different steps that we need to go through in order to perform on-chip debug. First, I'm going to generate a circuit. I'm basically going to come up with a circuit that we can debug. Then I'm going to instrument the RTL. After instrumenting the RTL, we're going to synthesize the circuit. We're going to run it at speed. And finally, we're going to perform our offline replay. So let's start here by generating the circuit. So for this specific demo, I decided to generate the circuit using LeFlow. And LeFlow is a tool that I actually created at the beginning of my PhD. And it basically allows you to go from TensorFlow to FPGA. And so you can basically write like 10, 15 lines of TensorFlow and we'll map it to hundreds of lines of RTL. And we basically made this possible by using Google's XLA, which actually outputs LLVM-IR, and we basically find a way of connecting this LLVM-IR to a high-level synthesis tool. So the takeaway here is that we can generate RTL from TensorFlow using some sort of high-level language. And this is the tool that we'll be using here for this demo. So for this specific demo, this is the network that I decided to create, very small network. So we have around 10 lines of Python code that describe it. So we have one output followed by convolution, followed by another max bool, another convolution, another max bool. We reshape this array, we have a fully connected layer, and then we have one output. And to make this here interesting, our input is only 28 by 28, but what we're doing here is that we're classifying between different drawings of fruits. I don't know if you ever heard of the Google Quick Draw dataset, but this is what we're using. So the idea here is that the user will be able to draw something here on the test screen. And as soon as this is drawn, this image is then sent to the FPGA. The FPGA has the DNN running on it, and the output is going to go to the 7-segment display. So if I go ahead and draw an apple, you'll see apple there showing up in the 7-segment display. Hopefully that's not too slow there on the presentation. If you go ahead and draw a pear, you'll see pear. If you go ahead and draw a pineapple, we'll show pineapple, and so on. So this is the circuit that we're going to be debugging today. And if you're interested about it, all of this code is also open source, and I can point you to the link later. Okay, so I already know which circuit I'm going to debug. So now let's going to instrument the RTL that has been generated. And a couple of things to note here. We're different from signal tap. We're adding the instrumentation directly on the top of the RTL, so we're actually able to examine the instrumentation if you want to. And also very interesting point here is that the circuit doesn't need to be HLS generated in order for our technique to work. However, if the circuit is HLS generated or it has been generated at a very high level, we can instrument it in an easier way, right? We know the schedule, we know how things in the high-level language are mapped to the hardware, so we can basically instrument things at a very high level. I can simply say, I want to observe this variable here in the Python, and then we can actually transform this into some sort of on-chip instrumentation. So this is exactly what we did here for this demo. So for this specific demo, I simply decided that I wanted to observe X, which is my input. I just really wanted to know if I was receiving those values correctly in my FPGA. And I decided to simply check whether each specific element of the array was 0 or non-zero. So that's the way that we're going to observe this input here. For some reason, I also decided that I want to observe the max bool after the first convolution. So I'm also going to observe max bool 1. And I also decided to have a look at the distribution of the input of the fully connected layer. And finally, just make sure that I know what my inputs correspond to, I'm also tracing the outputs using some summary statistics, right? So although we could instrument this directly on the top of the RTL by changing the RTL, I decided to instrument things here directly on the TensorFlow level. Okay, so we're then going to synthesize the circuit, and then we're going to run things at speed. So I can go ahead and I can draw a pineapple. The circuit will say pineapple, and once I'm done with this, then I don't need the circuit anymore. I don't need the touch screen anymore, just in the FPGA. Everything has been recorded there. And then I can start my offline replay. So I simply bring up my GUI. I press sync, and when I'm pressing sync, I'm basically gathering all of this information from the FPGA and putting it back in my offline analysis tool. And then I don't need the FPGA anymore. I can just perform the offline replay here. And what you can see here is that we have all of those different tabs. So you can see every single thing that I decided to observe. So we have the distribution, the spatial sparsity, some summary statistics. And you can see at the right side there, what are the tracked values for each of those instruments. So if I get rid of the distribution here for a second, and I simply look at the spatial sparsity and summary statistics, maybe I want to observe both the output apple and the output pineapple. And I can replay the execution over time. So I can see that things are changing as I draw it. Right around frame 25, I'm not sure if that's an apple or a pineapple, but as soon as I go ahead a little bit more, then I'm pretty sure, okay, yeah, that's a pineapple. So just showing that we are replaying the execution of what happened in the FPGA. But of course, this would not be interesting at all if I was just observing inputs and outputs. So one of the things that we can do here is that we can actually observe intermediate signals. So I can actually observe here the convolution after first max bool, which is also one of the things that I decided to instrument. And the takeaway here, what I want you to observe here is that even though I'm only tracing whether each specific element of the array is 0 or non-zero, I'm still able to see that something's happening there, and I'm still able to take some conclusions that might lead me to understand faster what the bug is. And to illustrate it a little bit better, let me show you one example here. Oh yeah, and of course, in this specific example, we decided to trace many, many different things. So all of this information is recorded and can be replayed in many different ways. Okay. So let me give you an example here. So let's say, for example, that I'm drawing a pineapple there, and the circuit really thinks that this is a banana, but everything has been trained before. I thought this was working, but my circuit, for some reason, is not working. So I want to figure out what's happening here. So I run things on chip. Oh yeah, and just so we know what's going on, I'm just going to tell you this. Let's assume that the bug is in the very first convolution, but let's assume that we don't know this, right? So we run things at speed. Every single information has been recorded on chip. We're going to start our offline replay. We're going to sync, so we're gathering all of this information, putting it back on our offline analysis tool. And then maybe we're able to see something like this. So we can see that our input is correct. I'm able to see the pineapple that I was just drawing there. But the output, it looks like it's all over the place. The circuit really thinks that for some reason this is a banana. So for now, I basically know that my input is correct. My output is complete garbage, and I can basically throw it away. So what I'm going to do now is that I'm going to observe something in between. And maybe the something in between here is the convolution after the first max pull. And I don't know if you can see this in here, but as I step through the circuit, you can actually see that there's something that is a little bit odd. Actually, all of the activations there, let's just wait until it comes back. There we go. All of the activations there, they're kind of upside down. So this can mean that, for example, I have an error in my RTL and I index things incorrectly. So I'm reading the memories in the wrong way. And this is causing things to behave this way, right? So now what we know is actually, I don't know if you can see my cursor here. So what we know is actually that the input is correct, but the max pull one here, the spatial sparsity here, this specific value here, it's not showing the right result. And the problem is that I'm not sure if the problem is in the subsampling here from the convolution one to the max pull, or if the problem is in the convolution from the input to this first guy here. And to really know what's going on, maybe I don't need to track this, this element here anymore, but maybe I really want to track this set of arrays here. And the problem with our instrumentation is that, or at least with this previous work, is that if we wanted to do something like this, then we'll have to add instrumentation again in the circuit, which is not a problem, but we'll also have to resynthesize the entire circuit to observe a different thing, which is of course a big problem because our debug iterations will take a very, very long runtime. Will take very long times, not runtimes. And this is why we created our second work, which is an overlay for rapid FPGA debug of machine learning applications. And the idea here is that we have a circuit and we're going to synthesize it only once, which is slow, but we're doing it only once. But the circuit is flexible enough so we can reconfigure it really fast and many, many, many times without the need of resynthesizing the circuit. And we basically decided to add three main things here to this overlay. Three main capabilities. The first capability is very simple, is a selective matrix tracing, which basically allows us to select which matrices in the user circuit should be traced. So this is very simple. It's basically like selecting, I want to observe this matrix now. Okay, I'm done observing this. I want to observe something else. So this is what you normally expect out of an overlay. The second capability that we decided to add is actually really interesting. It's the selective compression capability. And it allows us to change which compression scheme we're using in debug time. So this basically means that we're not only changing which of the matrices we're observing, but also how we're observing each of those matrices. And finally, we have the flexible trace buffer capability, which allows us to have a different allocation of the trace buffer space. So we can actually allocate the trace buffer space to instruments in a very dynamic way. So what this allows us to do is to store information about different parts of the circuit for different amounts of time. And if you think about it, this can actually be very, very powerful. So I can, for example, trace a signal that is very cheap to trace for a very, very long time because it gives me context of what's going on. And at the same time, I can trace specific information for a shorter period of time because maybe it's very expensive to trace that specific information. So the takeaway is that I can both have context while also having specific information. So this is the overall architecture here of our overlay. So at compile time, the user basically needs to select two main things. The first one is the number and type of the processing elements that will be used. And I'll talk about what those processing elements are in the next slide. And the second thing is the number of composable memory blocks. So composable memory blocks, you can think of them as simply blocks of on-chip memories that can be dynamically connected to the PEs in many different ways. So we can do interesting things, such as, for example, observing the same matrix in 3 different ways. Assuming that we have 3 instruments, we could have more. Or we could observe 3 matrices in 3 different ways. Or maybe I really care about observing one single matrix in one specific way, and I can use all of my composable memories to do it. So this is also a possibility. So this is basically what allows us to have that specific feature in which we can observe different things for different periods of time. So our processing elements are basically composed of 4 main things. They have some sort of instrumentation logic, which contains a compression circuitry. They have a reconfiguration block, which stores the settings that can be changed at debug time. They also have a matrix and memory selector. So this basically allows us to select which matrices to observe and also from which memory to read data from. And finally, we have a memory management block, which controls the reading and writing from those memories. The really interesting part here is the instrumentation logic. And the interesting thing here is that this instrumentation logic can contain either fixed logic or a flexible logic. A fixed logic just means that I can only do one thing. So the instrumentation can only either do the distribution of the matrix over time, or it can either record the raw values, or it can either record the sparsity of the matrix over time. You cannot change it debug time. However, a flexible logic can actually do many things. And we call our flexible logic a super instrument. And this is basically what allows us to implement the selective compression capability I mentioned earlier. So the super instrument here can change between distribution, spatial sparsity, and summary statistics at debug time. And in the second work, we also did some work on conceptualizing how the user would interface with this instrumentation. And now our GUI basically has 3 different purposes. So first, at compile time, the user can select the number of composable memories, the number and type of the PEs, and also which matrices may be traced. So we don't necessarily need to instrument the entire circuit. We can simply say we might be interested in tracing those specific matrices here. Then at runtime, the user can select which matrices should be traced at a given run and how the composable memories are allocated to the PEs. And finally, same as in our old work, at replay time, we can visualize the data that has been stored in the composable memories. So now let me show you some of the results. So this is a very simplified table of results, and you can find a complete table in our paper. This has been published at FPT last year. And the main thing here that I want to show you is that is the overhead in terms of the number of frames we're able to trace. So in this experiment here, we're tracing a single matrix at a time, either matrix A, B, or C, and those matrices have different sizes. And as you can see in the baseline in which each instrument is optimized to observe a specific matrix, I'm usually able to trace for more frames, of course, but I need to recompile every time that I want to change what I'm observing. However, in our instrumentation, we don't need to recompile, and our instruments with adaptive packing mechanism, they actually do a very good job using the memory space. Another thing that is not in this table, but is also interesting to know, is that the instruments from the baseline for this specific experiment here, they're never larger than 828 LEs, while ours are never larger than 976 LEs. So we have low area overhead, and this is basically because we're not observing many different signals throughout the circuit. We're only observing some few key signals. We're observing some few key matrices. Another thing that's interesting here is our super instrument, which is the instrument that implements the selective compression capability I mentioned earlier. And the key takeaway here is that it utilizes the memory fairly well, and the area overhead for this experiment is only 17% when compared to our largest common instrument. So a small area overhead for all of the flexibility it provides. So this is the conclusion slide for the debug overlay part. So here we basically presented a flexible overlay for on-chip debug. And this instrumentation is added at compile time and configure debug time, and it allows us to change which matrices will be traced, the compression circuitry scheme using the super instrument, and also how we are allocating the memories to the PEs. And the takeaway here is that we believe that the ability to change the debugging scenario without recompilation outweighs the disadvantage of the higher overhead. And now the summary for the entire talk is that we really believe that on-chip debug is essential. Some bugs may only really be diagnosed on-chip, and engineers do expect a complete ecosystem to design complex circuits. So we're not only talking about complete design tools, but also complete debug tools. And in our talk today, I basically show you that by specializing our debug instrumentation, we can store more useful information on chip, at least 21 times more useful information actually. And I also show you that we can provide debug time configurability at a very low area and latency cost. And with that, I'm open for questions.
All right, thank you for that excellent talk. We have time for questions. You may ask the question in the chat, or you can just shout it out, it's fine. Okay, so while we wait, I had one question, right? So for training, typically you would use something like a GPU rather than an FPGA. So I'm wondering, have you looked at what kind of debugging techniques might people use on GPUs? Would they use these sort of instruments compiled to CUDA and sort of spread them across, you know, the network stack, and then get those statistics in a similar fashion? Or you know, do you have any ideas of how you might get visibility when doing training using GPUs, and how an FPGA might be different in that context?
This is actually something that we are doing at this exact moment. So like very recently I did my qualifying exam, and I ended up working a lot of motivational examples, and this ended up coming out as one of the main things, training on FPGAs. And doing this comparison is actually something that we are trying to investigate right now. But one of the things that we're also focusing here is that we are also open to the possibility of a future in which we're actually someone like Microsoft that is using their FPGAs in large scale, and they're actually using FPGAs to not only run machine learning circuits, but also to perform research about very, very large machine learning circuits, right? So I'm also assuming here that there's also the possibility that we're gonna design and model those large machine learning models using FPGAs. So yeah, so the overhead of GPUs is something that we did not investigate yet, but it's something that we are currently working on.
Cool, thanks. There seems to be a question in the chat window. How large is the network you can fit with the debug? What percentage of the RTL circuit is computation versus debug for something like GoogleNet?
That's a very good question. So it really depends on the circuit, and really depends what we're observing. I think that a takeaway here is that traditional on-chip debug normally has a very high overhead, because you usually want to have visibility in terms of a large part of the circuit. Here, we are not tapping many signals. We're tapping very few signals, and we're observing them for long periods of time, right? So the overheads that we're seeing are very, very small. But to be fair, the circuits that we're playing with so far have also been small, but we're seeing overheads in terms of 2 to 3% in terms of area, and then the large overhead itself is in the memory, right? Like the huge challenge that we have is not area, but it's the amount of information that we're able to trace.
Okay. Maybe one other question I had was, what kind of assumptions do you make about how the matrix is stored inside the FPGA? So for example, my student and I, our accelerator sort of stripes a matrix across multiple block RAMs. Sometimes one block RAM or one URAM can contain multiple matrices. Yeah. Are you just monitoring the read-write ports to try and figure out, you know, this address range maps to this matrix, and that's how I'm going to compute the distribution or whatnot? And yeah, what would you have in mind if, you know, if the matrix is spread across multiple memory structures?
No, that's exactly it. So this is another. So you're exactly right. That's what we're doing. And the tricky thing here is that, so let's say that we are observing something that has been HLS generated, right? We know exactly how the high level C has been mapped to the RTL. We know how to instrument it. If you're creating something there by hand, then you basically will have to tell the tool, hey, this is how I'm storing the matrix. I'm storing it in those specific parts of the circuit, and all of this information together corresponds to a single matrix, right? So there is this overhead, this human overhead of basically saying, telling the tool what corresponds to what. And the tricky thing here is not only telling the tool that, but also in many different scenarios, the overhead of the instrumentation may depend a lot on how you're storing this information, because if you're spreading this throughout many different on-chip blocks, then out of a sudden I don't need to observe one or two things anymore. I need to tap many signals, so our overhead might be higher. So actually our overhead will depend a lot on the circuit that we are observing, right?
Interesting. Yeah, makes sense. We have one more question in the chat window from Kevin Song. Does the user have to worry about placing and routing the debug overlay?
That's a very
Does placing P's close to the module help or whatnot? Yeah.
Yeah, so as I said in the presentation, the idea here is that the user, so all of the instrumentation is added on the top of the RTL, right? So you are able to see the instrumentation there on the RTL, and the tool will take care of the place and route for you. This also means that if your instrumentation is very large, then you might have some sort of decrease. You, of course, increase your area a little bit, and you might also decrease your speed. So you have to make sure that you're not instrumenting a huge part of the circuit when you're doing this. But in terms of you going there manually and really checking where to place the circuit, I don't think that's how many people will use this. You're simply trust a place and route tool that will automatically put this there for you. Hopefully that answered the question.
Yeah, it looks like it did. Maybe one more question I had was, what kind of RTL bugs do you envision detecting with this flow that may not be detected in the TensorFlow environment or PyTorch or whatever high-level framework you might be playing with, right?
That's a very good question. So we're actually updating a lot our motivation examples because we noticed that machine learning is actually very repetitive, right? And this is actually a feature of machine learning. Like if you're doing inference, for example, you're basically always doing the same computation over and over again. So some bugs can quickly be seen in RTL. So we're looking at things such as, for example, performance debug. Sometimes you have non-deterministic behavior. You have something that changes a little bit, like maybe you're monitoring some sort of stalls. So if you're doing performance debug, you may want to do on-chip debug. If you're training and you want to have long-term visibility, this is another scenario in which you want to do on-chip debug for machine learning. And we're also exploring now, there are many papers that they are on understanding machine learning circuits, really. So basically understanding the interactions between the hardware and the model. And sometimes when we're doing this, we're actually gathering statistics over a large number of samples. So this is also something that we are investigating. So we're basically moving a little bit from debugging the circuit towards debugging machine learning model, understand machine learning model, and understanding performance issues in those circuits.
Okay, cool, makes sense. Okay, any other questions? Okay, I have one last question. So at a very high level, it seems like sort of the key idea here is, you know, the domain-specific nature of your instrumentation, right? That's sort of very powerful. Have you thought of applying it to areas other than machine learning?
No, not yet. The short answer is no. But the thing here is what we are doing for now has been domain specific, but not as much, right? We are basically tracking large matrices and trying to understand how they correlate with the model itself. But basically, you can use this instrumentation to debug anything that has very large matrices, and you think that recording statistics about it can actually help you debug. But we never really expanded this to other areas outside of machine learning. And if you have some ideas, I'll be very happy to.
Yeah, I'm just thinking off the top of my head, things like networking or databases, right, are increasingly sort of, you know, larger applications are being deployed in FPGAs using this technology. So for those kind of applications, maybe there's a family of instruments that are more sort of tailored towards the data structures used in those application domains. And I think, yeah, the idea of observing statistics is very clever, right? You don't want to look at raw data all the time. You might just want to see some sort of short signature, right? And that sort of makes this very interesting for other areas too.
Yeah, this kind of instrumentation is especially interesting if you have to observe things for a very, very long period of time, right? So like in any kind of problem in which you would assume that you have to observe something for a long period of time in order to understand where the bug is or like see where it manifested, then this is where you would use something like this. But yeah, I didn't think about using this for networking, for example, but that could be interesting. So actually a very good feedback. Yeah, thank you.
And then there's one last question, I guess, from the chat. Is it possible to concurrently collect statistics and show it in the UI so that you don't have to relay the onboard memory to store every frame? You have enough bandwidth to, essentially collect all the statistics at real time.
That's exactly it. So it all depends on if you have enough bandwidth or not, and also how you want to use that bandwidth, right? Like very often what I heard from people is that don't touch the network at all until I'm done. But very often I've seen papers in which they say that they opportunistically send this data via the network, right? And if you think about the way that we're doing this will also highly depend on the kind of statistic that we're tracking. So if we're tracing, for example, the raw values, very often it makes no sense at all to send this over the network, like it's gonna take forever. However, if you're tracing the sparsity of a huge matrix over a long period of time, and you only have like a small values, then it does make sense to send this over the network. But yeah, this is very application dependent, I would say.
Makes sense. Thanks. Okay, any other questions? Okay, if not, then let's thank Daniel for the wonderful presentation and the great answers. And I will see you guys next week. Thank you, Daniel.
Thank you for the opportunity and for the questions.